Pytorch, a dynamic open-source machine learning library developed primarily by Facebook's AI research lab, FAIR, provides a flexible platform for building and training deep learning models with ease. At its core, Pytorch offers tensors with GPU acceleration and automatic differentiation, enabling seamless development of deep learning applications. Its dynamic computation graph mechanism allows for intuitive and flexible model construction, simplifying experimentation and debugging. Pytorch's rich ecosystem of tools and libraries supports various machine learning tasks, including data preprocessing, model building, training, and deployment, while its Pythonic syntax and seamless integration with popular libraries like NumPy make it accessible to researchers and developers. Widely adopted in academic research and industry, Pytorch excels in applications such as computer vision, natural language processing, and reinforcement learning, thanks to its versatility, extensive documentation, and active community support, making it a preferred choice for deep learning practitioners seeking innovation in artificial intelligence.
Pytorch, a deep learning framework introduced by Facebook based on the Torch library, offers tensor computing with robust GPU acceleration, making it efficient for training neural network models. Its dynamic computation graph mechanism provides high flexibility and speed during model construction, while its Python-based interface ensures simplicity and ease of use. Pytorch enables developers to train neural network models in a distributed manner, and boasts a rich ecosystem of tools and libraries, facilitating seamless integration with popular libraries like NumPy. Moreover, Pytorch's versatility is evident in its ability to run on various platforms, including CPUs, GPUs, and specialized hardware like TPUs, as well as multiple operating systems such as Linux, Windows, and macOS. It can also be deployed on cloud platforms like AWS, GCP, and Azure, ensuring scalability and accessibility for deep learning projects across diverse environments. IT also seamlessly integrate with the Open Neural Network Exchange, ONNX format. ONNX is an open standard for representing deep learning models, allowing interoperability between different frameworks. Pytorch stands out for its Pythonic interface and dynamic computation graph, making it accessible for beginners. Its increasing industry adoption is attributed to its numerous advantages over TensorFlow. However, Pytorch lacks built-in deployment tools, relying on frameworks like Flask or Django. Nevertheless, it excels in performance and easily facilitates model training on multiple GPUs, enabling rapid prototyping and experimentation CF4.CF2. TensorFlow, initially with a static computation graph, shifted to dynamic graph computation with TensorFlow 2.0, further contributing to its extensive community support and widespread adoption. TensorFlow's strength lies in its production capabilities, particularly with the TensorFlow serving framework. However, achieving parallel training in TensorFlow requires manual coding and optimization of each operation. Nonetheless, TensorFlow boasts strong performance and efficient graph optimization capabilities. Overall, the choice between Pytorch and TensorFlow depends on specific project needs and preferences regarding ease of use, deployment, and production readiness. Pytorch operates by utilizing tensors, multi-dimensional arrays representing data, and computational graphs to perform operations and manipulate data. The core components of Pytorch include tensors representing data and computational graphs representing the flow of operations applied to these tensors. Unlike static computation graphs used in frameworks like TensorFlow, Pytorch employs dynamic computation graphs, allowing for flexible and adaptable graph structures. In Pytorch's dynamic computation graphs, nodes represent tensors and operations, while edges represent the flow of computation between them. During runtime, nodes are dynamically created as tensors, and operations are performed, and the graph structure can be modified on the fly, enabling seamless adaptation to changing requirements. This dynamic nature of Pytorch's computation graphs facilitates efficient experimentation and innovation in deep learning workflows, empowering users to create and modify complex models with ease. Dynamic computation graphs in Pytorch enable flexible model construction and optimization by allowing the graph structure to be modified during runtime. As tensors are created and operations are performed, nodes representing these tensors and operations are added to the computation graph dynamically. For instance, consider defining tensors x and y and performing operations like multiplication and addition, where each operation dynamically adds corresponding nodes to the graph. Additionally, the structure of the computation graph can be modified during runtime, exemplified by modifying the computation graph structure to multiply tensor z by 2 after its initial computation. This dynamic nature of Pytorch's computation graphs facilitates adaptive model construction and optimization strategies, empowering users to efficiently experiment and innovate in deep learning workflows. The Pytorch core encompasses the foundational elements of the Pytorch library. At its core, Pytorch revolves around 4 key components: the tensor computation block, modules block, graph block, and data loader block. First and foremost, tensors serve as the primary data structures in Pytorch, akin to multidimensional arrays, facilitating the representation and manipulation of data. Within the modules block, Pytorch provides an extensive set of predefined neural network layers, models, and utilities encapsulated as modules. These modules encompass parameters such as weights and biases and define the forward pass computation of neural networks, offering functionalities ranging from linear layers to activation functions and loss functions. The graph block represents the computational graph, dynamically tracking the flow of data and operations applied to tensors during program execution. Pytorch employs dynamic computation graphs, allowing for runtime modifications to the graph structure, which enhances flexibility and adaptability in model construction and optimization. Lastly, the data loader block comprises utilities for efficient data loading and pre-processing, including datasets, data loaders, and transformations, enabling seamless handling of training, validation, and testing data in machine learning workflows. Together, these core components form the backbone of Pytorch, empowering users to build, train, and deploy deep learning models with ease and efficiency. As we discussed in the earlier, Pytorch, tensors serve as the fundamental building blocks for representing and manipulating data, with different tensor types accommodating varying ranks or dimensions. Scalar tensors denote individual numbers, while vector tensors represent one-dimensional arrays of numbers. Matrix tensors extend this to 2 dimensions, forming tables of numbers, while 3-dimensional tensors encapsulate data cubes. Pytorch offers several methods for creating tensors, including direct initialization with specified values or leveraging built-in functions such as torch.tensor, torch.zeros, torch.ones, torch.rand, and torch.randn. Reshaping tensors in Pytorch is facilitated by methods like .view and .reshape, enabling adjustments to tensor dimensions while preserving the underlying data. Moreover, Pytorch supports a diverse range of mathematical operations on tensors, including element-wise operations like addition, subtraction, multiplication, and division, as well as reduction operations like sum, mean, and max. Linear algebra operations such as matrix multiplication, dot product, and trigonometric or exponential functions are also available. These capabilities empower users to efficiently process and analyze data in various forms, facilitating the development and optimization of deep learning models in Pytorch. GPU-based processing with Pytorch harnesses the immense computational power of GPUs to accelerate deep learning tasks, significantly enhancing performance compared to traditional CPU-based processing. At the heart of GPU acceleration in Pytorch lies CUDA, Compute Unified Device Architecture, a parallel computing platform developed by NVIDIA. CUDA allows developers to exploit the parallel processing capabilities of NVIDIA GPUs for general-purpose computations, including deep learning operations. Accessing the GPU through Pytorch is straightforward, requiring only a few lines of code. By checking GPU availability with torch.CUDA is available, developers can seamlessly switch between CPU and GPU processing. Pytorch tensors can be moved to the GPU for computation using tensor.CUDA or tensor.toCUDA, and back to the CPU with tensor.CPU or tensor.toCPU. To illustrate the performance difference, consider a matrix multiplication operation performed using NumPy, CPU tensors, and GPU tensors in Pytorch. While NumPy operates solely on the CPU and lacks GPU acceleration, CPU tensors in Pytorch provide flexibility but may not optimize deep learning tasks requiring extensive matrix operations. In contrast, GPU tensors leverage the parallel processing power of GPUs, yielding significantly faster computation speeds. This can be demonstrated with an example where the dot product of large matrices is computed using NumPy, CPU tensors, and GPU tensors, with GPU tensors exhibiting a substantial performance advantage over NumPy and CPU tensors. The Pytorch pipeline for creating a model encompasses several essential steps, each crucial for the successful development and deployment of deep learning models. Firstly, data preparation involves loading and transforming datasets using Pytorch's data loading utilities and transformations. For instance, loading an image dataset like CIFAR10 and applying transformations for normalization and augmentation. Secondly, model construction involves defining the neural network architecture using Pytorch's torch.n module class, specifying the layers and operations that compose the model. This includes defining custom layers or utilizing predefined layers from the torch.nn module. Next, training the model involves defining the loss function and optimization algorithm, iterating over the dataset to compute gradients, and updating model parameters through backpropagation. Following training, the model's performance is evaluated on a separate validation or test dataset to assess its accuracy and generalization capabilities. Metrics such as accuracy, precision, recall, and F1 score are computed to gauge the model's performance. Finally, once trained and evaluated, the model is deployed for inference on new data. Completing the Pytorch course marks a significant milestone in your journey of mastering one of the most influential and adaptable deep learning frameworks available today. Throughout this course, you've delved deep into the intricacies of Pytorch, developing a profound understanding of its capabilities and applications across various domains of machine learning and artificial intelligence. You've navigated Pytorch's comprehensive ecosystem, exploring its powerful tools and libraries. However, true expertise in Pytorch transcends theoretical knowledge and requires practical implementation. Hands-on experience is paramount to solidifying your understanding and enhancing proficiency with the framework. Therefore, we encourage you to continue honing your skills through practical experimentation, exploring diverse techniques, and leveraging Pytorch to tackle real-world challenges.